Alright, so this is Chapter 5, Part 2. We're going to start with bond order on the next slide. Alright, so now we're going to be talking about bond order. So, I have a couple example molecules set up for you guys, and so bond order is the average amount of bonds that a molecule will make with with another molecule. So, first we see the fluorine F2, so diatomic. It's F2 as fluorine or fluoride, whatever. Anyways, so it only has one bond, so it has a bond order of 1. Not too tricky, right? Well, oxygen has a double bond, 2 bonds. That makes it bond order. This is going to have bond order of 2. Nitrogen, you could probably guess this, has 3, bond order 3, right? Pretty easy. Sulfur is where it kind of gets a little tricky. Well, it does have 1, 2, 3, 4 bonds, but it's bonding with 3 oxygen atoms. So what's going to happen is you're going to divide the bond numbers divided by the amount of oxygen there are, and then you get 4/3 for your bond order. And there you go. It's a little weird because this one's 3 even though there's 2 molecules, and this one's 1 even though there's 2, and this one's 2 even though there's 2, but this is the example that it has in the Barron's book, so it must be right. Alright, here's something else I've never used, but just like bond order, but it is in the Barron's book, so I will touch on it briefly. This is bond strength, bond energy, and bond length. Well, bond strength, or bond energy here, is related to the frequency. So we see an equation in the Barron's book. It is E equals Planck's constant times, we get another weird V thing going. This is going to be a frequency of vibration, and so that will be bond energy. So just to explain bond vibrations, they're detectable in the infrared spectral region using a infrared spectrometer, and it so these studies have confirmed that single bonds have the lowest bond energy, and triple bonds have the highest energy, leaving double bonds in the middle. Well, this is I've never really seen this before in my experience during AP Chem, but I am touching upon it because it is in the Barron's book. The next thing they have is a little table. So they just show a couple bonds. I'm just going to do the carbon ones only because I don't want to draw all of them. But so they do that, and then they tell you the bond order, 1, 2, 3, right? Pretty easy. And they tell you bond length, 154, 134, 120. This is length in little picometers. I think that's what the P is for. I'm not 100% on that, so don't like yell at me if I'm wrong there. But and then we have bond energy, 347. That's ugly 7. 612 and 820. So this is E in kilojoules over mole. Alright, so the main point of this table, I think, is to reinforce that the single bonds are less energy, less strong. So you can see the molecules are farther apart when they have the Yeah, they're farther apart when they have only one bond, and then they have a lower energy. So it's really just reinforcing that a single bond is weaker than a double and triple bond. Alright, this is a section on nomenclature of some common covalent molecules. So as you can see, this is the molecule in the left column, and in the right column it is just the common names. Well, the only one I disagree with here, this is a table from the Barron's book, the only one I disagree with here is methane, because it calls it a trivial name, but it is following rules from for naming organic compounds, or organic molecules. It's organic chemistry, and you'll learn that later. But yeah, so that's the only one I really disagree with. So we're going to learn some rules for systemic naming. So it's really based on the number. It goes in order of what's in the, whoops, let me erase that, and kill that. Alright, it goes in the order based on what's in the molecule. So water, hydrogen, right? Well, there's two of it. So di is the prefix for two, hydrogen, and then there's one oxygen. So one mono, right? Oxide, hydrogen monoxide. Dihydrogen monoxide is water. Alright, methane is just, when it's the first molecule, you don't need to put the mono. If it's just one, actually many times you don't even see it at all. It's just in water, I guess. I'm not 100% on that, but you see carbon, right? One carbon. And how many hydrogen? 4. So tetra is the thing for 4. Tetra is going to go in the second row. Hydride. So as you can see from 1 and 2, they take the normal element like oxygen, and then they just make it an ide instead. So hydrogen turned to hydride, oxygen to oxide. Now nitrous oxide, you're probably like, oh, that followed the rule too. It has the ide ending. Well, the first part isn't right. There's 2 nitrogen, right? So it's going to be dinitrogen oxide. Alright, well, what about H2O2? Hydrogen peroxide? Well, it's going to be dihydrogen, right? There's 2 hydrogen. Dioxide. Alright, and the last one, hydrazine, well, has 2 nitrogen, 4 hydrogen. So, what do you think it's going to be? You said dinitrogen tetra, well, that was awful, tetrahydride, then you were right. So there are couple namings. Really, it's about reading the molecule and learning the prefixes for the amount of that goes with each number. So 1 mono, 2 di, 3 tri, 4 tetra, 5 penta, 6 hexa, 7 hepta, 8 octa, 9 nona, 10 deca. That's probably as high as you'll need to go, but it's very similar to the other prefixes we learned in I think it was the first video. So there you have it, naming and nomenclature. Alright, I've talked about this in previous chapters, but it mentions it in the Barron's book specifically right now, so I'm going to talk about it again. So here we have 2 oxygen molecules. Now, as you can see, they only have a single bond, so they're not stable. They're actually currently the peroxide ion, as it's named on the polyatomic ion table. Anyways, so as you can see, all their valence electrons, they're very straight around the oxygen. They make nice right angles. Well, when the second bond happens, we get that, right? Now, if you've been practicing drawing, you know this happens every time you have a double bond. It moves the valence electrons. Well, in case you hadn't listened to the other videos, you might think, oh, that's just how it's drawn. Well, as you can see, these angles, they're not perpendicular anymore. Well, what happens is the electrons that are part of the bonds here and here, so there's going to be 2 per, 1 electron, 2 electron, 1 electron, 2 electron, they are negatively charged. All electrons have a negative charge. Well, the negative charge on these electrons and on these electrons, they're going to repel. Remember, opposites attract? It's like magnets. So this repulsion pushes the electrons back, and that's why you get to see the slanted angles now, because they're being repulsed by the electrons in the bond. So this is just the basic push that you're going to start seeing now, and then I guess I'll draw a triple bond too, like nitrogen makes a triple bond. Now it's all the way on the opposite side. Well, it's pretty easy, there's only 1 pair, but the reason it can't be on top like that is because the negative charges here repel the negative charges there. So they want to get as far away from the bond as possible, whereas these ones want to get away from the bond as far away as possible without touching either, because they're also repelling each other. So that's why you start to see different angles on the valence electrons, and that's why that does not work. So this is just the start. We're going to get into some basic structures of molecules in a second, and it's like 3D geometry for drawing molecules. So these are the first of the 6 different basic geometry structures for molecules. Now, what you need to keep in mind here is that these are really the easiest ones, because these molecules don't have lone pairs. Once you add lone pairs in the mix, it starts pushing your bonds around, making weird angles because of the valence shell electron pair repulsion theory, which is the formal name for what I talked about in the last slide, where the electrons repel the bonds and vice versa. So these shapes also are named, so you should learn the names and the angles. So the first one is just 2 molecules, no lone pairs. It's a nice 180, so it is linear. That's what they call it. Well, the second one is also a straight line, so it's also linear. The third one, as you can see, it's not a straight line. It kind of makes a triangle shape, like sort of thing, right? Makes a nice little triangle. Anyways, this shape is called planar triangle. Now this happens because the bonds, right, they repel one another. Sorry, this is now getting kind of a messy drawing, but maybe I can kill that. If I go here, it's going to kill all the drawings before, but that's alright. I need to clear that up. Alright, so this is these are repelling, right? These are bonds, these are electrons. They don't want to be near each other. They're pushing each other apart, so it naturally spaces out like this because these are the angles at which the bonds can be maximally apart from the other 2 angles, or from the other 2 bonds. So this one is as far away apart from that one and as far away from that one as possible. Well, this one, if I can get a different color, it's far away from this one, it's as far away from this one as possible. And the same on the third. That guy is far away from that one and that one. So as you can see, I know I kind of mucked up the drawing, but it's the bonds are repelling each other, and that's why you see the 120. They're trying to get as far away from the other bonds as possible without getting, while maintaining distance from the the second bond. So this one's trying to stay away from both of those two. Alright, so these are the next two shapes, and to get into 3D, so you're going to need to visualize what's happening. So this, like shaded in triangle bond here, it is a normal bond, and it shows that the chlorine is, if you imagine it as a 3D thing, the chlorine is coming closer to you, while the dashed one means it's going into the back. And this line means it's staying just in a middle plane between those two. So if you just forget about this top part for now, it would make a triangular pyramid shape where there's that. So this is the CL, that's the CL up close, that one, and this is the CL far away, that one, and there's the carbon, and a final CL on top. But so that's what you're visualizing as a triangular pyramid with another molecule on top. So whoops. All right. Come on, tool. There we go. All right. So now what we're gonna do is I'm gonna tell you the name of this. This is a tetrahedron. And so this angle 109.5, I only drew it there, but it's between that and that, between that and that, between that and that. 3D wise though, so this angle here is curving out at you, while that one's curving out sideways, and that one's just kind of there, curving towards you at the top. This end's far away, this end's up close. Anyways, pyramid, visualize it, and that's the angle between all the bonds, so that angle there. Alright, the next one is a trigonal bipyramid, is the name, so I'm going to put that here so I have room to draw on the other side. Bipyramid. So this is, if you imagine a triangle, chlorine, that's the P, and so this part of the triangle that's in the distance has a CL, and this part's the one up close, so that has a CL, and this is the one in the middle distance. So it's a flat triangle that I can't draw it flat or else you wouldn't see it, but that's the shape you're imagining, a triangle that's flat towards you, and you're seeing the shape in the distance. So that is a trigonal bipyramid. Alright, so here's the final shape. This is the This is the octahedron. And so, if you're a little more used to reading these now, it's a square that's flat to you, so you really are signaling one side of the square this is realistic, but with two fluorines in the distance, two fluorines up close, then a fluorine above, that's going to be below, a fluorine below. Anyways, this is also a rare event where xenon is a noble gas that's bonding. So also we're going to look at bond angles. So from the fluorines that are above to this to the square makes a right angle. Well, also it's going to be hard for this to draw, but if this is the square, those are lines through. It's not an accurate square, but that would be a right angle also. And that one. So all the bond angles on this one, 90 degrees. So these were just examples of the 6 basic structures, and every molecule that has the same amount So if we go back to the first one, I use hydrogen-hydrogen just because easy and no valence electrons, or no lone pairs, I should say. The thing you need to worry about that will change these is the lone pairs on the central atom. So, for example, if we do water, H2O, oxygen has two lone pairs that push the bonds inwards. So whereas before, our three-element one was still a nice line of carbon, sulfur, sulfur, carbon didn't have any lone pairs, right? Well, oxygen, the central atom here, does have lone pairs, which, when we learn about the valence shell electron pair repulsion theory, pushes these bonds angles in, making this, instead of a nice 180, maybe like 120 or 117, hard to say. Main point is, these shapes, the 6 basic ones, will work for any of the molecules that, for any molecule that has a corresponding number of atoms involved, but without lone pairs on the central atom. So I know it's a lot of information, but it's not even half of it overall, because in the next section I'm going to have to teach you all the ones with the lone pairs. So get ready. Okay, so now your book is going to derive structures, and these are the they're built off the other 6 structures that I showed you, but now the atoms have lone pairs. The central atoms have lone pairs, which changes the shape slightly and usually drops one of the atoms. There's a really good table in your book that in the Barron's book, in my edition, it's on page 193. Again, I have the 6th edition, and it's going to be most handy. So I'm just going to draw and then label the shapes based on their derived structure and their shape, and then the different atoms that can go in them. So this is the first one. It is linear, and it is a diatomic atom, so it's really just 2 atoms, and it's going to make a line every time. Doesn't really matter where the lone pair is, because any 2 points can make a line. Alright, this next one is called bent. If you remember, we had the other time we had 3, it made a nice straight line. Well, this time there are lone pairs there and there, and it pushes, remember the repulsion between the lone pair and the bond angle, it repels it, making this a nice bent angle of 120 degrees. So that's why you get that bent shape. So just some things I forgot to do, and you can see the XE and the X2E. This is just showing that, like for example, the linear could be made with 2 of the same elements bonded, hence the X2, or 2 different elements, so XE, where X is one element and E is the other. And the X3, so this shape could be made with 3 of the same elements, or 2 of the same and a different third. Or the chlorine could even be replaced with something like fluorine or bromine, really just anything that would actually bond with it. And here's the triangular bipyramid. So again, this is it's similar to before. We had the other pyramid shaped one. Is the tetrahedron. Well, this time you have a lone pair here instead of another H atom. And this is going to also have a 109.5 angle, just like the tetrahedron did. And also, before I move on to the next slide with more structures, I'm going to address an error I made on this molecule. There's only 1 lone pair, but the tin, it's a 2+ ion, or it's not the ion I thought it was, so just forget one of this is there. So this one is also the bent shape, and you're probably wondering if this is why this is AX4 again? Well, there's another way to do it. Before we had 3 of one element and 1 of the second. Now we have 2 of each element. Now you're probably wondering how 2 of each element is represented in the oxygen. Well, the oxygen has 2 lone pairs instead of just 1, which makes it count as 2. Think of X as the amount of other elements, and you can think of E also as the amount of lone pairs on the central atom. So, yeah, that's even the way I would choose to read this notation is A is one element, X is the second element, and then E is the amount of lone pairs. This shape, I'm not going to write it down because it's too long. It's a distorted tetrahedron. I personally never use this shape, and yeah, it's not common that you'll ever have to draw this one ever. Usually the ones that you have to draw are the tetrahedrons and the triangular pyramids. That one's pretty common. And a couple of the regular ones. Bent obviously comes up a lot. Linear too. Square pyramid, square planar. There's some shapes that are more common than others. This one I'm going to put an X because it's not common. So this one makes what's obviously called the T shape. It makes a clear T. This one also very uncommon. So I wouldn't worry too much about the last two. They are quite rare. This one you'll see every now and then. It's when you have 3 atoms and 3 lone pairs. Anyways, these 3 lone pairs the top one kind of cancels out with the bottom ones a little bit in repulsion, so you get another linear shape. And that's why this one is also linear. That's awful writing, but E-A-R, linear. Alright. So this shape makes a square pyramid. If you can imagine it actually standing up, it'd be something like that, or you get a square base. This is going to be like a fluorine, 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 and then fluorine on top, and the iodine would be somewhere in the middle of this, like in the middle of the shape, with a lone pair directly beneath it. And that's what this would look like, so that's why it's called a square pyramid. This one also not super common, but also not super rare, so you should know that one. This is the last shape we are doing. This is the square planar. It just makes a nice little square. As you can see, it is quite similar to the pyramid, except it replaces the top limb with a lone pair. And there you have it. If you want the shapes that I just make from having the notation in the far left side, those will be the shapes, the not derived structure shapes, the basic structures. So like the AX6 would normally make an octahedron, but when instead of having 6 fluorines you have 4 and 2 lone pairs, this shape is a square planar. So again, 3D drawing, pretty important. It will be a good portion of your test if I remember correctly. I had to draw a good amount of molecules also, and learning to draw them will help you visualize them better and learn bonding rules better, because you can see the atom, you can see how it bonds a lot better in your brain. Alright, so now this is just some practice with drawing and moving it up to the next step, which is drawing a whole molecule. So here is a molecule. It is propane, which you will learn the naming for later when you do organic chemistry. All I need to know right now is there's 3 carbons and 8 hydrogens. So we're going to draw this guy. Well, first we have CH3 to draw. So C. Now we know this C is going to bond to another C, so we'll just do that there. So you have that. So now if we have a bond and 3 other molecules to draw on, what shape does it make? Well, if you've been practicing, it makes a pyramid, one of those pyramid shapes. So can I have 1H coming at you, 3D, 1H normal, and 1H going off in the distance. So that's your first molecule. Now, CH2 doesn't have any lone pairs or anything. So what's that make? That makes a nice linear shape. And another CH3 makes another pyramid. So now this doesn't always happen this way, but it is more common that the hydrogens will tend to not line up, like they'll line up opposite, so that the I'll draw this isn't a super important thing, so if you don't get it, don't worry about it, but this hydrogen and this hydrogen will tend to not line up, so that's why that one's going to the distance and this one's up close, just because charges, and especially when it's on a like a molecule where they're up close, and I had a hydrogen here and a hydrogen here, one here and one here, these two would definitely not be on the same plane. They just the molecule tends to rotate around the bond so that the hydrogens are not in the same linear plane as the other hydrogen. Again, not important, not super important, and you probably won't be marked down drawing it with them going in the same plane, but just a little side note. First rule of determining the polarity of a molecule just by looking at it. This is a CO2 molecule that I drew down here for an example, but the rule is if it's symmetrical, it is nonpolar. So, for example, this molecule has 2 oxygens. They're the same element on each side, and they bonded in the same way, so it's nonpolar. Each one has a dipole moment, which you would think make it polar, but A, it is a small dipole moment of 0.8, but B, and more importantly, they're going in opposite directions, and they're the same size of dipole moments. They're the same size dipole moments, which are these green arrows, and because they're going in opposite directions, they cancel out, making CO2 nonpolar. The next rule is that a non-symmetrical molecule will be polar if the bonds are polar. So here is HCl. It is polar because chlorine has an electronegativity of 3.2, water has electronegativity of 2.2, giving it a nice 1.0 for dipole moment, which makes it polar, and there's no other dipole moment to cancel it out. It's a non-symmetrical molecule, so no more dipole moments, it makes it polar. So the next rule, I'm using a drawing here, is that a central atom with different kinds of atoms bonded to it will often be polar. So for example, I used it's methane, but one of the hydrogens is replaced with a chlorine. And so, you'll learn naming later again in organic chemistry. I'm not going to worry you with it right now, but the chlorine has a different dipole moment than the hydrogens do. They have much smaller ones also going this way, but because it's not symmetrical and it has a different element here, the polarities are not even of equal length, so there's a large moment going that way, making this a polar molecule. This is the last one, the last rule you can use, and it is a central atom with lone pairs. These little guys will be polar. Well, you're probably thinking, hey, water is symmetrical, So it should cancel out, or moments that way, they should cancel out. Well, again, lone pairs. The lone pairs, very negative, and they're only on the oxygen atom. Also, if you know a little bit of more about electron sharing and covalent bonds, you know the oxygen atom is bigger than the hydrogen atoms and hogs the electrons more because they tend to gravitate towards the oxygen, which has a higher mass. So you see that the oxygen, she gets a bit of polarity, making water polar. And this is again largely because of the lone pairs on the central atom. So if a central atom has lone pairs, it is often non-symmetrical and polar. So now at this point, this video is also getting pretty long, and there's still a good amount of stuff left to cover in Chapter 5. Chapter 5 covered a lot of basics, and a lot of really important stuff for chemistry, but they also require pretty good explanations before you can really understand the whole thing behind them. So, we are left, Chapter 5, Part 3 is going to cover hybrid orbitals, and we'll talk about that. It has to do with bonding and the way they share electrons. So, tune in for Part 3.